Building a modern metropolis from the ground up provides a rare opportunity to optimize for a specific goal, the removal of every unpredictable human variable. Mainstream attention often centers on standalone humanoid androids. However, the engineering reality in Xiong'an moves the conversation to a deeper layer, an urban-scale operating system that treats the entire city as a single piece of hardware. This multi-lane road is part of a 500-kilometer digital network. Below the surface, engineers have embedded 20,000 sensors designed to translate physical movement into a constant stream of machine-readable data. These data streams converge at the Urban Computing Center. This facility acts as the city's physical brain, processing 33 billion records to maintain a digital twin, a virtual mirror of every building, pipe, and vehicle in the city. Visibility is achieved by assigning a unique IPv6 address to every physical terminal. By tagging everything from a street lamp to a delivery pod, the system can track and manage the city's hardware with the same granularity as code in a server. This connectivity allows the system to execute what engineers call a 15-minute lifecycle. The city brain monitors resource demand and autonomously recalibrates traffic signals and delivery routes down to the millisecond to maintain a constant state of peak efficiency. By automating these micro-decisions at a velocity that outpaces human reaction times, the city creates a closed loop. Human intervention is functionally slower and less precise than the system's own logic gates. Maintaining this velocity requires overcoming the physical constraints of latency. When multiple robots navigate a high-density intersection, even a standard 5G connection to a distant cloud is too slow. A few milliseconds of lag can cause a physical collision. The solution is edge computing. As shown in this comparison, processing the signal at a local node, like a sensor inside a lamppost, allows for an instantaneous response that prevents the crash. By shifting the processing power to the street level, machines enter a state of agentic AI. They no longer wait for a centralized command. They assess the local environment and execute physical decisions independently. In this architecture, human oversight is reduced to passive observation. These operators monitor the massive citywide display, but the actual operational choices are being made by the edge nodes on the street. A flawless software layer is only half of the equation. To manifest this logic in the physical world, the system requires a massive volume of cheap, vertically integrated hardware. These hardware specifications emphasize a strategy of rapid deployment over isolated perfection. While some firms focus on perfecting a single, expensive Android, this model prioritizes modular units that can be integrated directly into a citywide 5G network. Success is driven by vertical integration by design. Handling hardware, firmware, and AI within a single industrial ecosystem allows engineers to prototype and deploy new designs at a pace that global competitors struggle to match. The density of these automated workstations shows the result of this strategy. These are not high-cost prototypes. They are mass-produced units designed to fill labor gaps at scale. The real leverage comes from cost efficiency. Using low-cost, mass-produced components, like a 10-cent plastic gear, allows for the deployment of entire fleets for the price of a single traditional Western robot. This combination of cheap hardware and an omnipotent OS creates a new blueprint for urban labor. In this environment, the cost of automated deployment can drop below the cost of a human salary. This pursuit of efficiency creates a systemic vulnerability. A city engineered to remove human decision-makers has no one physically present to manually override the system when it fails. This is the engineering reality of cyberkinetic warfare. When a city's physical movement is governed entirely by code, digitally jamming the network translates directly into physical paralysis on the streets. A single error in the operational tech, what developers call dead code, can cause a robotic joint to seize mid-motion. In an interconnected system, one locked joint can cascade into a wider systemic freeze. The stakes are binary. A single point of failure in the city brain doesn't just crash a server. It halts the logistics, the transit, and the entire physical economy of the city. Hyper-efficiency removes the human buffer. The result is a state of systemic fragility, where the entire urban machine is only as reliable as the last line of code. The robot city still accommodates human residents, but their status within the system is being redefined. Traditional urban commerce, like this market in Beijing, is a human-driven process. It relies on messy, chaotic, and highly adaptable human interactions to function. Xiong'an operates on a different logic. Here, autonomous delivery robots move through sterile, predictable streets without human intervention. People are no longer the drivers of the system. They are biological janitors, kept on standby purely to maintain the hardware when the automation falters. Xiong'an is a shift in urban planning, where human presence is secondary to technical efficiency. It is an architecture designed for the machine, where the human variable is gradually optimized until it is no longer required.